So number 4.
She's been ignoring me all day, and as soon as I got on the computer, she just needed attention.
Huh?
Freya? Freya, who is that? You here? You just got so needy
Oh.
all of a sudden? So needy? Oh,
She's like, yeah.
she's so funny because like she's an affectionate cat,
Uh-huh.
but there's some things that she hates. Like she loves just being held like a toddler and squeezed on your shoulder.
Uh-huh.
But my cat Wednesday, like
Uh-huh.
you can hold her like a baby, like literally on her back and just hold her like a baby, and she
That's
actually
what.
likes that.
Yeah.
But Freya hates that. So Alex, my brother, will pick up Freya and like hold her on her back and like go in for kisses, like she's a little baby, and she literally like will just hiss at him. Like she sticks her paws out, sticks her paw on his face, and if he goes in for a kiss, she'll literally hiss.
That's that's how I hold my cat as like a little baby. But I think it's because I've been doing it since she was like a little baby, so she's used to it. But
Here's Wednesday. And
oh,
Wednesday is like the limpest kitty I've ever seen. I swear she's like part liquid. Wednesday? Wednesday? You see Sarah? You want to get a
hi.
good close up?
Oh, I love cats.
Oh, Wednesday, you're so sweet.
Where's my cat? I'm like, I need some love for my kitty.
Wednesday is like the most chill cat I've ever met. She's so just low maintenance. She just needs hand licks occasionally, but aside from that, like I think I've literally heard her hiss maybe 4 times, and I've had her for almost 4 years.
Really?
Yeah, she hissed. I took her to her vet, and she had to get an antibiotic shot. She hissed at that. She hissed at me one time when she was freaking out because she got she was under the sink and got a plastic bag from like Smith's or something wrapped around her leg. And so
Uh-huh.
the rustle was freaking her out. So she's just running around, which made it rustle even more, which made her freak out until she hid under my bed. And so I was trying to grab her and I was like trying to get her out from under my bed so I could take the bag off of her leg. And that just freaked her out. So she hissed at me. And then I'm trying to think. She hissed. I don't know. Like she's a super mellow cat. Like literally, I've had her for 4 years, and she's hissed in the single digits. Like nothing
Yeah,
ruffles her.
such a good cat. I love cats. Everyone should just have a cat. Oh man.
Okay, so how are bar charts and Pareto charts related?
The only difference between a bar chart and a how do you say it?
Uh,
Parili?
I've been pronouncing it Pareto.
Pareto chart is that the bars in a Pareto chart are ordered largest to smallest going from left to right.
Okay.
Pareto.
Was that in the reading? Because I honestly don't remember that.
Yeah, so it was actually in the Excel, and they one of the steps I actually have it right here. It says click on sort largest to smallest, and that's and then your bar chart should be converted to a parallel
Okay.
chart. Yeah, so
Okay.
it was from the Excel instructions.
That makes sense. Okay, so the next 3 questions, we conclude that p hat is normally distributed. So what's p hat since we're working with new symbols for pretty much the same definitions we've been doing all semester?
So p hat is the sample proportion.
Yes. So the probability of our sample. So
Yes.
as opposed to the probability of the population. So in essence, p is mu, p hat is mean. So kind of how we've been So
P.
like how we've been using throughout the semester just to distinguish rather than saying the mean of the population and the mean of the sample, we've just
Mhm.
been saying mu and mean.
Yeah.
P, just regular P, would be related to mu, so it's the population, and then p hat would be the equivalent of mean or x bar.
Okay, that makes
So does
sense.
that make sense?
Yeah.
Okay. Because yeah, like I said a lot of times, it can just get really wordy if you say out. We conclude that the distribution of the probability of our sample is normally distributed. Like that's just freaking hard to say when you can just say we conclude that p hat is normally distributed.
Yeah, way easier. Way
Yeah.
easier.
So yeah, so p hat is sample, which means it's akin to mean, and then p regular is the mu when it comes to probabilities.
Gotcha.
Okay, and yeah, this is what I was talking about. Our n needs to be so np needs to be equal to or greater than 10, and n1 minus p needs to be equal or greater than 10. So that means if we have the lowest n we can possibly do is if it is a 50-50 shot, because zero point 0.5 and 1 minus zero point 0.5 is still going to be 0.5, and
Mhm.
that means 0.5 we divide both sides by p. That gives us n is greater than or equal to 20. So
So do we always
the
we
absolute
always
lowest sample size we could ever use is
uh-huh.
20, and that's if we're using a probability that occurs 50% of the time. But as probabilities change, like rolling a dice, the odds of getting a 6 when you roll a dice is 1 in 6. So we
Okay.
would have to do 10 divided by 1/6, which is equal to 60. So in that case, our sample size would have to be much larger in order to ensure that p hat is distributed normally.
Okay.
Does that make sense?
Yeah, so actually I have a question. So I know what P stands for and I know what N stands for, but what does NP stand for?
Oh, it's
Never never
just
really said in the reading.
yeah, no, that's just lazy math. That should be n asterisk p or n times p. That's an equation. That's n times p.
Uh, okay, that makes so much more sense. Okay.
Yeah, so what that's saying is that your sample size times the probability of your instance occurring has to be greater than or equal to 10.
That makes so much more sense. I was like, what does NP stand for? I'm like, okay, sorry. That was a blonde moment. I should have known that.
Oh no, no, you're totally fine. The fact that we use so many symbols, they really should they really should have put like an
They should,
asterisk in there or the
yeah,
times, you know.
yeah, they should have done that because I was like, man, what does NP
But
mean?
knowing that does that make sense? Like think about it. So if we look at NP
Mm-hmm.
has to be equal or greater than 10, if P is equal to zero point 0.5, flipping a coin,
Mm-hmm.
we divide both sides by zero point 0.5 to get rid of P. 10 divided by zero point 0.5 equals 20. So our sample size needs to be 20 or greater. Does that make sense?
Yes.
And
Okay.
then, like I said, rolling a dice. Rolling a dice would be you want to go for the low end because that's just going to show us how high we need to. Um, yeah, we want to look at the lower number when it comes to the probability of something occurring and the probability of something not occurring
Mm-hmm.
because we want to make sure that our sample size is correct. So let's say again the dice roll, the odds of getting a 6. The odds of getting a 6 is 1 in 6.
Mm-hmm.
So we divide 10 by 1/6, and that means our n has to be 60 or greater. Whereas if we look at n1 minus the probability, that's going to be 5/6. And so that would end up being both sides divided by 5/6. So 10 divided by 5/6 is going to be 60 divided by 5, which is 12. You see that there's a huge difference between
Yeah.
the answers. We always want to make sure that we find the one that requires the higher. Like the standard is you do both equations, and then you choose the higher of the two ends.
Mm-hmm. Okay. Okay. Gotcha.
Okay. And then, so is P the true proportion, or the population proportion, I guess you could say, or the sample proportion?
The population or the true proportion.
Yes, because what are we calling the sample proportion?
T with a hat or T hat or P hat. Are
But I have seen T hat. No, I've
you
seen, yeah,
serious?
I've seen T hat. The most commons are T hats, P hats, I hats, and J hats.
Oh,
I can't even remember how those popped in, but I've seen those.
little did I know that it was an actual thing.
Well,
Look,
when you're dealing with the same dealing with the same syllable so many times,
hmm
you have to come up with ways to distinguish it. So you got X and X bar, you got P and P hat. Like
hmm
there's a lot of little things that they do to change it so they can reuse the same symbol over and over.
Yeah.
Okay, so this one's easy. What is N?
Sample size.
Yeah. So even though we're dealing with probability, that's like the one thing that hasn't changed. Okay. So I gave you the explanation just a minute ago. Using the two equations that were given, if p is equal to 1/4, what is the smallest n that satisfies the requirement?
Okay, so okay. Okay, so I guess I'm gonna talk my way through this. So I'm going to times what I do point because 1/4 is 25.25, right? So
Mhm.
yeah, okay. So I would times it by 10, which is 2.5.
Would you times it?
Divide it. Divide it.
Yes.
So that's 0.025.
Mm, you went from timesing to division, and division is correct. You got your numerator and denominator switched.
Oh, do I?
Yeah, so we're looking at the equation. The sample size times the probability of it occurring equal is greater than or equal to 10. So if we want to get n by itself, what do we do to both sides?
Right. We have to divide it.
Divide by what?
0.25.
Yes, yeah,
Okay, so
perfect.
it'd be 40.
Yes. Yeah, you
Okay.
just had a little dyslexic moment and divided by 10 instead.
Yeah.
So, but yeah, you totally got that.
Okay. And
And then
so,
just to double check, what about the other equation? Because we got to make sure we're choosing the higher of the two ends or the
yeah.
larger of the two ends.
Okay, so we would do. And is n always 0.5? Or do we not need to
What
know?
is n?
Oh, I guess we don't need to know.
Yeah, we're solving for n.
Right. Okay. Is it 13.3?
I think so. Let me double check.
Okay.
Yeah, that's what I got.
Okay. Whew.
So we'd want to just choose the larger of the two ends because that is going to ensure that it's normally distributed.
Okay. So even if it says what is the smallest, we still do we want to put 13.3 for question
Well,
7?
it's saying what is the smallest n that satisfies the requirement. What it means by that is NP
Mhm.
must be greater than or equal to 10. So it's saying it's normally distributed if it's equal to 10 or greater than 10,
Okay.
which means if we want it to be normally distributed, 40 would be great, 41 would be great, 42 would be great, 80 would be great. Anything larger than 40 would be great. So that's why they had to specify the smallest n.
Okay. Okay. So 8.
So n equals 24 and p is 0.4.
Is equal to P. So the mean of P hat is P.
Yes.
Wait, 0.4. Easy.
What does that mean? Um, what does that mean in English?
Um, okay, so the mean of P hat is the mean of the sample. And so um, the mean of the P hat is equal to P of the population. Hmm. Wouldn't that depend on the sample size? And they gave us a sample size.
But as you notice, the sample size, we could have an n equals 24 or n equals 1 or n equals whatever.
Mm-hmm.
Um, this is how it changes with probability. So let me know if this makes sense to you.
Okay.
So just stop me if what I'm saying is confusing.
Okay.
But for example, if we're dealing with going back to heights of people, to find the true population mean, to find the true mu, we would have to know everybody's heights and then divide that by 7.6 billion people, and that would give us the true mean.
Yeah.
And then we compare our x or x bar to that, and we see how that compares. And if you remember theoretically, um, the more sample sizes we take, and it doesn't even matter how big n is, n just decreases the standard deviation.
Deviation.
But as long as we take a lot of samples, whether the sample sizes are 3 or 30 or 1,000, as long as we take a lot of samples, there's going to be a distribution curve of our samples, right?
Mm-hmm.
And as long as we take enough, if we just take a lot of samples, then it's just going to be one of the laws of statistics that the mean of our means, so the mean of x bar,
Mm-hmm.
is going to be equal to mu.
Yeah.
That's just a law of stats.
Yes.
Here is we already know the probability. So think of this not as zero point 0.4, but think of it as again flipping a coin. The odds of getting heads when you're flipping a coin is zero point 0.5. And so it's a 50-50 shot.
Yeah.
When we're dealing with p hat, so when we're dealing with samples and the distribution of the samples,
Mm-hmm.
think about any individual sample, especially if it's a low sample. You'd say that the probability of flipping a head is going to be 50%, right? Let's say you have somebody flip a coin 3 times, and they flip a coin 3 times, and each time it comes up tails. So that means the probability of flipping heads for them was 0 as opposed to zero point 0.5, right? And that's because I was a small group. But the thing is, even if you do only do 3, even if you have a sample size of only 3 and have each person flip a coin 3 times, if you have enough people flip the coin 3 times over and over and over again, it's going to be the same result as before, where all of that averages out. And so you're going to have a distribution of some people getting all tails, some people getting all heads, a few mixes in there. But once you get enough samples, um, the p hat, so the mean, the sample mean is going to be exactly equal to 0.5, which is the population mean, the mu. So does that make
That
sense?
makes sense. Yeah, I mean it's the same concept as you're talking about as the mean and the mu, and we did that little exercise where we typed in, we got to see all the graphs and stuff. So it's kind of that same concept except for with P and P hat.
Exactly, yeah. Yeah, the only difference is that when it comes to probabilities, it's a lot easier to know the true probability than it is to know mu. Because
Hmm.
yeah, like I said, knowing the average weight of all Americans, you'd have to weigh over, what is the population? 300 million. You'd have to weigh over 300 million people and then average that out.
Hmm.
Whereas if you have if you have an honest dice, so it hasn't been tampered with anyway, we automatically know that the probability of rolling a six is 1 in 6. We
Yeah.
know the probability of rolling a one, two, or three is going to be 50% because that's three of the options out of six.
Hmm.
So probability, it's a lot easier to know mu for probability than it is for other things. So we're going to see the mu, in this case p, pop up a lot more than we have in previous chapters because it's a lot easier to know p than it is to know mu.
Okay. Yeah.
Does that make sense?
Yeah. So it's like easier. I'm cool with that.
Yes. Yeah. So yeah, and so like you were saying before, if you as long as you take enough samples, it doesn't even matter how big the sample size is. As
Mhm.
long as you take enough samples, x bar will our mean will always be equal to mu. And in this case, it's just saying the same thing but for probability. If you take enough samples, p hat is going to be equal to p.
Okay.
So same concept.
Gotcha. Okay. So 9. What is the standard deviation of P hat? Okay. So.
This is like the first new equation we've seen in a while. Because
Yeah.
everything else, when it's a new equation, they just say do it on Excel. Do you
Hmm.
remember the equation for this?
Yeah. So it's all under the square root, and so it's
Mhm.
P times parentheses 1 minus P and parentheses over N.
Okay. So totally right. Putting those symbols into English, how would you phrase that?
uh. The population times
What's the well, where's population fall in this?
I guess the probability of.
There you go.
Okay.
So probability times what?
Times 1 minus probability
Which is
over
also known as
uh oh p hat.
no,
Wait,
but
1.
I can see what you're going for. But what do we know? Let's say what do we know about probability? There's a few things that we know about probability. Can probability be less than zero?
No.
So you can't have a negative probability. What's the absolute largest probability can be? One. So we know that probability has to be between 0 and 1, right?
Yes.
So that means probability is always, um, what's the word? A real number, a fraction, whatever. It's not an integer. That's the thing. It's always a real number between 0 and 1, which means it's a fractional number.
Hmm.
Um, so we know that 1 minus p is also going to be a fractional number, and that those two numbers up to be 1, right? Do you remember that from like it was like in the first 2 weeks? It was saying that the probability of something happening plus the probability of it not happening is always equal to 1.
Yes. Yes.
Yeah. So that's what this is saying is this equation is the probability of something happening
Mhm.
times the probability of it not happening divided by the sample size and take the square root of that.
Okay.
And sometimes they're going to be the same. So, for example, flipping a coin, it's going to be the probability of it happening, getting a heads is 0.5. The probability of not getting a heads is going to be 0.5. So it'd be zero point 0.5 times 0.5 divided by the sample size. Other times you'll get rolling a dice. Probability of getting a 6 is 1/6. The probability of not getting a 6 is 5/6. So it
Hmm.
would be 1/6 times 5/6 divided by sizes.
Okay. That makes sense.
Okay,
Gotcha.
so knowing that, what's the standard deviation for p hat?
Okay, so let's see here. So we're gonna do 0.4 times 1 minus 0.4 um, divided by 24. The square root of that is so 0.1.
Give me 1 second. That sounds
Okay.
about right. The square root. Yeah, I got 0.1.
Sweet. Okay, so 10.
Following information for the next 4 questions. Brittany's batting average is 0.3. We want to determine the probability she will get more than 35 hits in her next 100 bats. N equals 100, P equals 0.3. Okay, so Brittany's batting average is P. So that would basically be the probability for the population. So even though we're just talking about one person, we're
Mhm.
talking about
The
her
whole,
entire batting career.
yeah.
So that's every time she's been up to bat, she's got a batting average of 0.3. So now
Okay.
we're looking for a sample of her next 100 bats. So
Okay.
the sample size is her next 100 bats, and we want to see what is the probability that her batting average for the next 100 bats would be 0.35 instead of 0.3.
Okay.
So does that interpretation of the way they explained it make sense?
Yes. So the p hat would be 0.35.
Exactly.
What's the standard
And
deviation?
standard deviation.
So okay, so are you doing 0.3 parentheses 1 minus 0.3 or 0.3.5?
Okay, so what's the equation for standard deviation?
So it's p times um 1 minus p.
So p hat
So
isn't even in the equation.
okay, so okay. Okay, I got 0.0021.
Let's see. That is lower than what I got. Um, what numbers did you plug into the equation?
Okay, so I put zero point 0.3 parentheses 1 minus zero point 0.3 and parentheses divided by 100.
Oh, there's the problem. So when you're done with the probability and the n, what's the last step that you do?
Uh, I um
Because you're like
put it in
90% there. You're just forgetting the last step. Look at the equation again.
Oh, square root. Gosh dang it.
There you go.
I was like, wait, oh, I better be careful with that. Okay, so it's 0.046
That's
rounded.
what I got. Yeah, perfect. Okay, so the z-score. So let's do this as if we were doing a z-score that's not probability, just to kind of show the way it goes. So what would our mu be?
Let's see. So our mu would be 0.3,
And our x would be?
would be 0.35.
Perfect. And we also know the standard deviation and the n. So what would our z-score be?
Okay, so we uh okay. Hold up. I don't think this is right. Negative 5.523.
That's not what I got.
Okay.
Here's a
So
here's a quick thing to just double check. So what's at the top of the z-score equation?
P hat minus P.
Okay. Our
So we
p
would,
hat our p hat is larger than our p, right? 0.35 versus 3.
yes.
So that right there tells you that if you get a negative z-score, you've done something wrong.
Okay, so I put, so I did the top of it first. I did, 0.046. Oh, oh, that's what I did wrong. Duh.
Mm.
Hold the phone. I'm smart. Okay. Okay. 1.087.
Oh, sir, I got something a little bit different,
Okay.
but I could be the one wrong here. So what's the numbers that you plugged into the equation?
So I did 0.35 minus zero point 0.3,
Mm-hmm.
which I got 0.05. And then I divided that by our standard deviation, which was 0.046, and I got 1.08695.
Okay. So it sounds like you totally did it right.
Okay.
What it looks like, and this is why I prefer Excel. It looks
Excel
like
is
it
accurate.
looks like it was just a rounding error.
Okay.
Because the standard deviation I ended up using was
Hmm.
0.045826. And then that got plugged straight into the equation. So
Okay.
like Sister Cook says, don't round until the final step. And that's what I like about Excel is
Hmm.
that you can plug everything together and then it'll just give you that final answer and then you just round it to in this case 1.091. That's what I got. Really
Okay.
close to what you got. So 99% positive that that was just a rounding error.
Yeah. So you got 1.091 is what you said? Okay. Cool. As long as I'm doing the math right, I'm like, okay. Okay, so 13. What is the probability where it gets at least 35 hits in the next? Okay.
Okay, so looking at this, um, just deciphering what they're saying, the probability that Brittany gets at least 35 hits, we know her Z score is 1.091.
Mm-hmm.
When we put that Z score in the probability, interpreting gets at least 35 hits, what part of the curve are we going to be looking at?
The right side?
We're going to be looking at the right side or the right and middle?
The right in the middle.
Why would we be looking at the right in the middle?
Because at least, so it could be
What's another
like
way of saying at least?
um greater than or equal to.
So we're seeing what's the probability that the number of hits she gets is greater than or equal to. So if we're looking for greater than our Z score, what are we looking at?
Just the right side.
Yes. When would we be looking for at the right and middle side?
Um, oh, um, hold up. I totally know this. Isn't it? Oh, equal to.
No.
Wait a second. I totally know this. Not equal to is highlight the two tails.
Yeah, not equal to is highlight the two tails. Greater than we're looking at to the right of the Z score.
Mm-hmm.
Less than we're looking at the left of the Z score.
Mm-hmm.
So if it's one tailed and we're including the middle, why are we including the middle?
If it's greater than or equal to.
Not necessarily. I know you know this, so I'm trying.
Positive Z-score.
There you go.
Okay. I
If we
was like,
if
what?
if we had if we got a negative Z score, if we got a negative Z score, so let's say that instead of 35, we were wondering what was the probability of her scoring at least 25,
Mm-hmm.
since that's equal distance away from 35, you know?
Mm-hmm.
So if we got a negative Z score and we're looking at least, or in other words, equal to or greater than,
Mm-hmm.
we'd still look at the right side, but the bar would be the negative Z score bar. So that would be the middle and the right side.
Okay. Yeah, that
So,
makes sense.
so I hope I didn't confuse you because you're completely right with your first instinct when you said we're looking at the right tail of the curve. So you're
Yeah.
totally right on that. Did I confuse you, or
No,
does that all make
no, no,
sense?
no. That's
Okay.
a good reminder of the applet because we didn't use it these past couple weeks. So
Yeah.
yeah. Okay. So what is the probability? So do we enter the z-score into the applet then for
hmm
this?
Yeah. That's
Okay.
how we
So it's
use the
gonna
normal
be
probability.
0.862.
What'd you just do right there? Because I can totally see what you did without even seeing your screen.
Uh, I don't know. I don't know what it is.
What areas do you have highlighted?
The right in the middle,
What do we want highlighted?
just the right.
Yes. Because our Z score is positive. So we're looking for greater than a positive Z score, which means that we don't care about the middle.
Okay. So it
So
would be 0.138.
yes. So
Okay.
yes, it's pretty rare to happen because we're always looking for outliers.
Hmm.
But if you're looking for greater than a negative Z score or
Hmm.
less than a positive Z score, that's when you include the middle.
Okay. Makes sense. Okay, so 14. What is the standard deviation?
Okay, that's just a quick calculation.
Whoa.
What'd you get?
Oh, really long number.
Really long number and what?
Well, okay, wait, I need to
Really huge or a lot of zeros?
lots of zeros.
Okay, I already know what you did wrong.
Oh gosh dang it, what did I do?
What's the last step of the equation?
Square root. Dang
There you go.
it.
If you square
Okay.
root a super tiny number and it becomes less tiny.
Yeah, you know me too well. 4, 8. Okay, so I think I put enough zeros. I think it's like 3 0. Okay, so 0.011.
Yeah, that's what I got.
All right. What score would you use? So you would do. Okay, wait, I'm confusing myself. Um,
So what's the equation for z-score? It's the same as before, it's just that we're using p and p hat instead of x and mu.
yeah, so p hat minus p over the standard deviation.
Yes.
And so what's p hat in this one? It's the same as p, right?
So you read the question, the true proportion to support the candidate is p is equal to 0.52. The question we're wondering was
Oh, it's 0.5.
exactly what's the probability of them getting less than 0.5?
Okay, that was just me not reading the full question. Okay, sorry. Okay, so negative 1.818.
Another rounding error. I got negative 0.1790. At least I'm assuming that's a rounding error.
Yeah, so I did
Because I've
point.
got zero point 0.5 minus 0.52, so it's negative, and the standard deviation I've got is 0.011171. So I've got a pretty precise standard deviation.
Okay. Yeah, so I just got my standard. Yeah, I got negative 0.02 divided by 0.011. So yours is right. Okay, so what was it? You got negative 1 point.
790.
Okay.
Okay, and this last one, the probability of the survey results to show the candidate losing, even though the true p-value is 0.2, so this is just going to the applet. We go to the applet, our z-score 0.1790, and which part of the applet are we looking at here?
So we're looking at what is the probability the survey results will show the candidate is losing even though the true. So we're looking at the left-hand side.
Yes. When would we look at the left-hand side and the middle?
If for this problem it would be um like, what is the probability that the survey results will show the candidate losing or tying with the other candidate?
No, it just comes down to the numbers we've gotten rather than phrasing the question. So remember, the only time we include the middle
Mm-hmm.
is if we are looking at, let's see, if we're looking at the probability that's pretty much against the z-score that we got. So in this case, if we're looking for less than, so less than 50, if we're looking for less than, but we got a positive z-score. So if we would have got 1.79, and then the flip side, we would check the middle if we were looking for greater than, but it was a negative z-score. Then again, we'd be looking at the right side, but we'd be looking at the right side of the left bar. Conversely, we'd be looking at the left side of the right bar. So you always have to keep in mind
The z-score.
yeah, you always have to keep in mind what we're looking for, less than, greater, or two-tailed. And you
Mm-hmm.
also have to keep in mind the z-score.
Z-score.
90% of the time, Sister Cook hasn't thrown a question at us where it's like, what's the probability of getting less than, but we get a positive z-score,
Uh-huh.
Like, she hasn't done that to us yet, but there's always the chance that it will happen.
Yeah. Yeah.
You're completely right. Describing less than just means you're looking at the left side of the graph. The greater than means you're looking at the right side of the graph. Whether the z-score is positive or negative
Mm-hmm.
lets us know to the left or right of which line we're looking at. So the z-score lets us know, okay, we're looking at the left line or we're looking at the right line. And then if we're looking for less than or greater than, that lets us know if we're looking at the right side of the graph or the left side of the graph. Does
Okay.
that make sense?
That makes sense. Yeah.
Okay. Yeah, Sister Cook hasn't tried to trick us with that yet. I
Mm-hmm.
do think I remember seeing it in a homework though. I don't
Oh,
recall,
yeah.
I don't remember seeing it in any of the quizzes or tests, but I
Mm-hmm.
do think I saw it in a homework. And there's always the probability that she'll throw a curveball in there just to make sure that you understand
He likes
conceptually.
to do that.
Yeah. So what'd you get?
Okay, so it would be 0.037.
Perfect. That's what I got. Okay, so I'll submit real quick. And that is 100, so you're safe to submit.
Ooh,
And
love it when
if
we
we scan over, see if we can find her. Where are you?
Aww.
Wednesday, where are you? Oh, there you are. There you are.
Aww.
She's just watching me do my homework.
You're such a good kitty.
Wednesday, are you just so protective of me? Such a good kitty.
Oh my gosh, I love cats so much. Um, so the study, uh, should we like divide that up or
Let's talk about that on Thursday.
okay.
Um, I'll go through the worksheet a little bit more. I'll see if the study that we talked about, if there's any reason we wouldn't be able to use it.
Yeah,
But honestly, that's one that sounds simple enough, and it does have some kind of interesting implications
it's awesome.
um, of the subconscious. Kind
Yeah.
of like things that you're not really thinking about. So I'll go through and look and see if that isn't something we can do.
Mhm.
Um, if it isn't, then we'll come up with something else. If it is, then on Thursday we'll figure how to divvy it out.
Okay. Perfect. Sounds good to me.
Okay, then I will see you on Thursday.
Cool.
Okay,
See
see ya.
ya.